So now we're recording so we can get started. This is 3.1, so you're going to appreciate chapter 3 after doing all of that stuff in 2.7 and in 2.8 with the definition, because now we're going to fly. That stuff that would take forever is going to just be a quick second. So one of the things that we're going to start off talking about with derivative is the derivative of constant. So what the derivative is finding the slope of the tangent, correct? So if we understand that, whenever we have a constant, what kind of a line is like y equals 7?
Straight line.
It's a straight, but it's a straight horizontal line, right? And since it's a straight horizontal line, what's the slope of that horizontal line?
0.
0. So it makes sense that the derivative of constant would have a slope of
0.
0. And it's important that we understand it graphically, right? So like I said, if I had f of x was equal to 7, if I go to graph that, that's going to be something up here. And we see that the slope of this is in fact 0. So in this function, we end up seeing that our slope is 0. Okay? The next one that we're going to talk about is the power rule. And it's pretty sweet. So the power rule tells us that if we have something to some power, right, as long as it's a real number, typically our powers are integers, but if it's not, it doesn't matter. We still do the same thing. We'll take that power, put it in front as a coefficient, and then subtract 1 from the power, and that will give us our new number. So if I gave you the simple one that we always do, right? If this is f of x, the derivative of f of x then would be bring the 2 out front, go 2 minus 1, and this is going to give us 2x to the first power. Make sense? If I had done something different, so let's say I had done just a little bit more complicated. Let's say I would have done, I don't know, it's funny, I'm doing an example and there's an example right below. So this one's obviously going to be 3x squared, right? But let's say I gave you something like 2x to the 4th. What's going to happen is the derivative of that is then going to be the 2's out front, but then the derivative tells me bring down the 4 and then go 4 minus 1. So I'm going to get 8x to the 3rd. Does that make sense? That power drops down from the power rule, and then we just subtract 1 from the power, and that will be the derivative. Instead of going, okay, the limit as h goes to 0 of f of x plus h minus f of x all over h, that's much more complicated, right? So we've just learned how to save ourselves some time. Thank God for Leibniz and Newton, right? Those guys really saved us some time. Okay. Going on to the next thing. So a normal line is perpendicular to the tangent line. So you'll use this a lot in physics. So as you all are sitting in your chairs, I assume you're sitting in chairs, what's happening to your bottom is the chair is pushing up on you with the same amount of force that your body is pushing down on the chair. That's called a normal force. And the normal force is always perpendicular to the surface. So with a normal line, it's always going to be perpendicular to the tangent. So I'll give you just a quick picture. We've done this a ton of times, right? Where we have this y equals squared, and then I went, here I'll use blue. If I have a line that goes this way, right? That's my tangent line. My normal, I can draw this very good. My normal line is going to be perpendicular to the tangent. So this would be the normal, while this is the tangent. Always 90 degrees. Okay? It is what we call, instead of perpendicular, we call it orthogonal in mathematics. That's just some fancy word. Okay, so let's do an example. What's an easy number that we could use? I don't want to go crazy. Let's just use 1. Okay, so our P, let's just use 1. So if we say when x is equal to 1, we can find out what's going to be perpendicular to that. Okay, so we're going to take the derivative of this to find the tangent. So the tangent of this is going to be 3 over 2 times 8x to the 7th, correct? Which will clean up to be 6x to the 7th, right? And then we're going to evaluate that at x equals 1. So that tells me that my slope for the tangent is 6. Do you guys agree with that? Or did I do that too quickly?
Why do we evaluate it at 1?
Because I told you I'm giving you a p-value of 1.
Oh, okay.
If I'd have said at 2, you evaluate at 2. If any number that I give you, that's what you evaluate it to find out.
But if we weren't, if we weren't given a number, we would stop at 6x to the 7th?
Yes, that's the general case of the curve 3/4 x to the 8th. But in order to be able to find a specific normal, we need to have a point on a line, a point on a curve, to be able to find the normal.
Okay.
Right? So this would be the tangent. Then to find the normal of this, we know that the normal slope would have been I'll put normal down below, would be a negative 1/6, right? Because what do we know about perpendicular slopes?
It's like the opposite reciprocal.
Opposite reciprocal. So now that we know what the normal slope is, we need to be able to go find the point. And so to find the point, we know it's going to be 1, 3/4, correct?
Mm-hmm.
So our tangent line would have been y minus 3/4 is equal to 1 times x minus 1, while our normal would have been y minus 3/4 is equal to a negative 1/6 x minus 1. And I just put these in point-slope equation form, but those are the equations of the two lines. You can put them in slope-intercept form quite easily from there, right? We're good?
Yeah, makes more sense.
Okay, cool. So this is the tangent line, and this is the normal line. Any questions?
I have a question.
Yes, absolutely.
So, Professor, so what's the utility of this normal line?
So that's a great question. I kind of shared a little bit about it, but typically what ends up happening is normal forces in physics is when we really use it, right? Finding tensions that are used that are going to keep something in a position where we want it to stay in place. So if we have something like a curve like this, right, and you can't really tell, but gravity's coming straight down, right? So that's going to make that thing sag. So a normal force to keep it in this straight line needs to be used to keep this thing straight. Does that make sense?
Yes.
So case in point, even with like I said, sitting in our chair.
Right.
When you sit in your chair, if there's not a normal force pushing up, guess what's going to happen to you?
Fall down.
You're going to fall. You're going to break the chair.
You'll literally sink.
Yes. So there are normal forces that are used all the time. When you walk, there's a normal force that's applied every time you take a step. The amount of mathematics that's involved in our daily lives is insane. We just don't think about it.
I see.
Yeah, like people, yeah, I used to always love when my students be like, when am I going to use this? Like in algebra, I'm like, dude, do you ever buy stuff? Like 3 pairs of jeans. That's math. Don't you want to know that you have enough money, or you just want to walk up to the counter and be embarrassed? Like, um, now the advent of credit cards has complicated that, but then you need to be able to do the math that's algebraic to be able to calculate, hey, how much am I paying in interest on these credit cards? Is it worth it to buy this stuff? You know, I always talk to my students about that. If you buy something for $100 and it takes you 5 years to pay for it, you've basically paid double for that thing. Well, depending on the interest rate, maybe even more. So credit cards are the devil, my buddies.
I had a question for this example.
Sure.
How'd you get the -1/6 for the normal line?
Okay, cool. So since I know that the normal is perpendicular, I know that perpendicular, when I find the slope of the tangent, the normal slope has to be the opposite reciprocal. So opposite, it was positive, now it's become a negative, and then the reciprocal of 6 is 1/6.
Okay.
Does that make sense? So
Yeah.
just remembering, whenever you have tangent, the normal is going to be the opposite reciprocal of it.
Okay.
Do you want me to make another one for you guys to try?
Sure.
Okay. No worries. So here's another example. I don't know. Give me any equation you want. I don't care. Anybody want to give me an equation?
X equals 5x to the power of 7.
Okay. Well, we want it to be something that, how about 5x? You said 5x to the 7th power?
Yeah.
Okay. 5x to the 7th power plus x, you said? That's fine. I don't care. Give me a number to plug in.
Like to be from the P?
Yeah, to be your p, to be the x coordinate for your p.
3.
3? All right, so you want us to deal with some big numbers. Cool. I'm going to need a calculator because I'm pretty good at math, but I don't know 3 to the 7. So let's see. 5 times 3 to the 7th power plus 3. Okay, so the point that we're going to get is 3,10938. So 10,938. Now what we're going to do is we're going to take the derivative of this guy, so it's going to be f prime of x is equal to 35x to the 6 plus 1, correct?
Yeah.
That's the derivative. And now we need to apply the derivative at that
X
point.
is going to turn into 1, right? If it's just an x by itself.
So when x is by itself, the slope of x is 1. Yes.
Okay. Yeah, 1 of them.
Because the power is, so here's what, it's a great question. Let me just side note this, okay? If I have x, that's the same as x to the first power, right? So if I follow the power rule, I'm going to get 1 x to the 1 minus 1. So I'm going to get 1 times x to the 0, but what's x to the 0?
1.
So it's 1 times 1, which is 1. Okay?
Yeah.
Just side note. Okay. Now we need to evaluate this at, we need to evaluate this at 3. So I'm going to go 35 times 3 to the 6 plus 1 is 25,516. That's f prime of 3. Okay? So that's our slope. That's a steep slope when x is 3. So then the equation of the line for this one would have been y is equal y minus 10,938 is equal to 25516 x minus 3. Got it?
Yeah.
And that's the tangent. Correct? That's our tangent line. Now the normal is going to be the reciprocal of that. So then I know that the normal is going to have a slope of 1 over 25516 negative. And my equation is going to be y minus 10, 9, 3, 8 is equal to a negative 1 over 25516 x minus 3.
Question.
Yes.
So it says x equals 3, and you don't plug that into the second x in the original problem?
Are you talking about right here?
No, the first part, like 5x to the 7th plus x. So when you bring that down, you don't plug in 3 to that second x?
To this one?
Yes.
You have to take derivatives first.
So I took the derivative from here to here, right?
Yeah.
And then when I plugged in 3 there, I got this number. So I did plug into this. That's why I have f prime of 3.
Plus 1 instead of plus 3?
Well, because what's the derivative of x?
Oh.
It's 1. That's why there's a derivative symbol there. So I went 5 times 7, and then I took a power away, making x to the 6th. The derivative of x becomes 1. So this is the derivative. Now when I plug in 3, I'm going to get this as the slope of this curve, at 3. Does that make sense?
Yeah, complete.
Okay.
Thank you.
Yes. And then over here, I plug in 3 into this to get the actual point where the curve is. So the actual point where we're finding the tangent is at x3, y 10,938.
Got it.
Can you say that again? Sorry.
Yeah, no problem. So let's go first things first. In this function, right, we're evaluating at a p value of 3, correct? I'm going to plug in 3 into the original equation to find the point where I'm trying to find the tangent. Does that make sense, America? Okay. It was you that asked, right, America? I did it, or was that Carol who asked it?
Yeah, I understand that. That got me like messed up because I was following along, but then I just like.
No problem. So this is the point. Then this is the slope of the derivative. And now this is the slope of the normal. And the slope of the normal is always going to be the opposite reciprocal of the slope of the tangent. We good? Just making sure. I don't want you guys being lost on these little details and then it harming you later. Okay. So can I move on? Okay. Something that we have, and we pretty much already did this. So when we have the derivative of a constant times a function, that's the same as going the constant times the derivative of the function, which we did in that previous example. So all this is saying is if I have 4x to the 5th, if this is my function, I can go 4 times the derivative of x to the 5th, and that's going to be 4 times 5x to the 4th, which will give me 20x to the 4th. You guys, we did that already, but just reinforcing the rule. Okay? We also did the next one, it's the sum rule and the difference rule. All this is saying is if you have the derivative of a sum of functions, that's the same as the derivative of each summed. And we did that, right? So if we did a derivative of, like, I don't know, x squared plus 3x, that's two functions, right? X squared is the f of x and 3x is the g of x function. We can take the derivative of each individually. Don't worry, we're never going to do it this way. But it's just showing you that this is derivatives. So this becomes 2x, that one becomes 3, and that is the derivative of x squared plus 3x. Rocket science, right? People, it's funny. This really is rocket science. It's the math that starts us analyzing that stuff. It's all been rocket science. Okay, the difference, same thing. There's nothing special about it. So if I took that example that we did before, but instead of having a plus, I made it a minus. And we see this is going to be 2x minus 3. That's the only difference. It isn't crazy. Is anyone feeling overwhelmed? Yes, this lecture is being recorded. So no worries if you have to go or if you're doing work or whatever. I am recording it so that it will be posted for you guys. Yeah. Okay. The next piece is e to the x. Everyone makes a big deal about the number pi. E is, okay, no problem. E is a function that its derivative is the same as its y value everywhere. That's so cool. So the derivative e to the x is in fact e to the x itself. So what it's basically telling me is if I have the graph e to the x, right, which looks something like this, what's so cool about this is if I take a point, like let's say at e to the 0, what do I know about e to the 0, my friends?
Is it 1?
It's 1. Now what's cool is if I go back and take the derivative of e to the x, I'm going to get e to the x, and then when I evaluate it at x equals 0, I'm going to get the same y value. So whatever the y value of e to whatever number is, that is the slope of the curve of the tangent. Isn't that cool? So e to the x ends up being pretty special. We should have a February 7th day off. Or like they have pi for 3.14, people have pi that day. I don't know what we could do for E, but we should say.
I remember in my middle school on Pi Day, they had us like basically go through the entire lecture how we went. They basically taught us how they discovered pi, and then we had pi at the end.
Yeah, they make such a big deal about it, but e to the x is actually pretty special too, but no one ever gives it its due. You're gonna fall in love with e to the x. It's rad. Okay, so anytime you see e to the x, the derivative of e to the x is something fun. So if I gave you something like, okay, if I gave you a function like 5e to the x plus 7x plus, let's make that squared, plus 2x, the derivative of this thing is there's no change here. This becomes 14x plus 2. E of the x. You guys want me asking 10 questions on the derivative e to the x for the exam? It makes it really, really easy for you to be successful, which is cool, right? Okay, I think that's it for, I think that's it for 3.1. Do you have any questions for me or anything that you'd like me to clarify while you guys have me here? Just trying to make sure, because I want you guys to be as successful with this stuff as possible, and so I'm available. So any questions before I go into 3.2? Okay, let's go into 3.2. One of the things too is you guys knew that I had office hours this morning, correct? Okay, I was on, no one came on. So if you do have time available in the mornings and you want to get one-on-one time with me, the office hours are awesome because no one ever shows up. And to be honest, I just sit here in my office at home like this. Oh God, can someone show up? So the hours are on. They're on the Canvas under modules where the videos are. There's a one underneath that titled Office Hours, and that has a link with my office hours on there. Okay. You can go. Yeah.
Because I went to the office hours yesterday, like at 1:15.
Mm-hmm.
Were you able to go, or was I in the wrong link?
No, so you were the only person that went on there. I got that email. Like I said, for some reason my computer was having issues yesterday, and so I wasn't able to get on my office hour yesterday. But I did see that you were on there. I get an email anytime someone shows up. So yesterday, for those 30 minutes when you were on, I couldn't get on my computer. But on my phone, I got an email that you were waiting for me.
Oh, okay.
So you were in the right place.
Cool. I was just worried that I didn't have the right link or something.
No. So the link that I have on there is right. It was just...
okay.
Yeah, that's why Apple's sending me a computer tomorrow. Because...
nice. Cool.
I just... Yeah, no problem. I deleted a bunch of stuff off my computer because all these videos that I'm recording, they take massive gigs. And so it's like my computer gets bogged down. And so I need a new computer with a bigger memory. Like right now, I have an external terabyte drive on this computer, so we don't have issues today. But I don't want to be doing that all the time, you know? So, okay.
Nice.
So yes, you had the right link, and Carol, cool. I'll see you tomorrow for my office hour. Let's go on to 3.2. All right, here's 3.2. All right, 3.2, product rule. This is going to be very, very useful. You're pretty much going to have to memorize this, okay? And here's how it works. So when we have the product, what we end up doing is we're going to do the derivative of the first times the second plus the first times the derivative of the second. Okay, that's a tedious way to remember it. I don't want you to remember it that way. So I wrote it in a simpler form down below, and you just need to know this. So it's the derivative of the first times the second, meaning functions, plus the first function times the derivative of the second function. Right? And this is just to save us time, because if we don't, it becomes pretty tedious. here's an example for you guys to be able to see. So if what I could do with this example is instead of having two functions there, I could have expanded these two functions and multiplied it all out by distributing and then taken the derivative. But you can see that's a lot of work, right? I don't want to do that much work. And so typically when we have two products, what we want to do is we want to follow these rules. So what I'll do to help you guys is I'll do it in color. Actually, it's almost Christmas time, so I love Christmas. I like gifts and stuff, so it's cool. I usually end my lectures by saying Christmas, right? Or when I solve a hard problem, you'll just hear me randomly say Christmas. That's just the weird person I am. So anyways, with this thing then, we're going to take the derivative of the green. So the derivative of the green is going to be 8x times 7x cubed plus x. And so that stays the same. The green becomes this. That's the derivative piece, right? Plus the first, not changed, right? And then the derivative of the second. And the derivative of the second would be 21x squared plus 1. And there's that. Okay? So we see it f prime times g, f, g prime. Are we okay with that? Are there any questions?
Question.
Yes.
How did it become 8x?
Oh, cool. So from here, right, this green one, what's the derivative of a constant?
0?
Perfect. That's 0. So we have 4x squared. What's the derivative of x squared?
Oh.
You see it?
Yes, now I see it.
Yeah.
Okay.
So then the x squared
I
becomes
need more
2x.
coffee.
What's that?
I need more coffee.
No, for sure. I mean, I already had coffee during my hour and a half office hour by myself. So I had a couple cups of coffee. So
Oh, fancy.
yeah.
Thank you.
Yeah. So look, that's the whole point. When you guys ask these questions, if I can get those aha moments for you guys where it makes the connection, that's everything to me. Because then you're really learning this stuff, right? Okay, so now from here, we want to clean this up. And we do want to be deliberate about cleaning it up. So we're going to distribute and do all that stuff to this problem. So we're going to go, okay, that's going to be 56x to the 4th plus 8x squared, right? Plus, and then we're going to go 4 times 8, or 4 times 21 is 84. X to the 4th plus 4x squared minus 21x squared minus 1. Okay, then we need to combine like terms. 56 plus 84, those are like terms. What's that going to be? 90 plus 50 is 140, I believe. I'm trying to do this all in my head. Plus 12x squared. Oh, minus 21. I almost forgot the minus 21. So that's going to be minus 9. Is that right? Minus 1. Can you guys verify that? My algebra could potentially suck, and I don't want to get it wrong.
Yeah, that's right.
Okay. So this would be the derivative of this product. Do you guys want me to give you one to try?
Yes.
All right. So let's do this. Here's an example for you. How about we find the derivative of 3x cubed plus 4x . . 4x . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . times 2x squared plus 3x. All right, try that one. I just made it up, so hopefully it's not crazy. Let me know when you're ready. Okay. I'll demonstrate it and then, follow along and see if you're along the right track. So we're going to go derivative of the first. So the derivative of the first would be 9x squared plus 4 times the second, right? That's our g of x. Plus, it's the first, so that should be 3x cubed plus 4x times the derivative of the second, which should be 4x plus 3. Is that what you guys were able to get? And again, let me just... You guys got that? Okay, cool.
Yes.
I like the thumbs up, Ray. Nice. Okay, so then from here, just color coordinating so you guys can see which one I'm working with. Now I'm going to try to expand these. So I'm going to get 18x to the fourth plus 27x to the third plus 8x squared plus 12x plus 12x to the fourth plus 9x to the third plus 16x squared plus 12x. I hope my expansion is correct. I think it is. So I should get 30x to the fourth. Looks like 36x to the third plus 24x squared plus 24x. Right?
Correct. That's what I got.
Yep.
Any questions on that?
No.
Just want to make sure that we're all okay. Anyone need to have me show how I did the distribution there? So yes, Carol, these problems, they look easy, and I'll tell you, eventually these little rules that we're going to do, I'm going to make derivatives that end up looking so crazy hard, but they're all little steps. So if you take them as little steps, they're really not that bad. But you're right, it looks easy, and then all of a sudden it gets crazy hard. But you'll get there. You'll get there. Just imagine when I do a product with a quotient, it'll get even more complicated. Maybe I'll do one of those at the end so you guys can see how tough this can get. Okay? Do you follow at least the process that I'm doing here? Okay. All right, that's good. Good. Okay, let me show you another rule, and this is the quotient. And the quotient rule is actually not too bad here. I'll leave that there so people can see. The quotient rule is really not that bad. The way it works is it's going to be the derivative of the top, or what we call the numerator, times the denominator minus, and that's the big thing, it's a minus here, the numerator times the derivative of the denominator. All of that divided by the denominator squared. So I should do it this way just to be a little bit, so you guys can see it a little bit cleaner. Okay? Now, I don't ever write it that way, so I do it this way. Now, something that will be useful for you guys in terms of the exam, if you understand 3.1 and 3.2, you'll be able to check your work on the exam for this exam 1, knowing these shortcuts. Does that make sense? So when you do the limit as h goes to 0 of f of x plus h minus f of x all over h, and you come up with an answer, you'll be able to use power rule or whatever rule that we're doing to be able to see if you're getting the right answer. So this should confirm what you're getting. Does that make sense? So it's giving you a tool to be able to check your work. All right. May I do an example? All right, here we go. So again, I'm just going to color coordinate. So when I set this up, what I'm going to end up getting is, I'll write it down just so you guys can see, and then I'll clean it up. So that's going to give me 2x, x to the 4th plus 1, minus x squared minus 1 times 4x cubed, all over x to the 4th plus 1, that quantity squared. So that's this one, it becomes this, and then that's the f function. What ends up happening here is this was f prime, this is g, here's f, this is g prime, and then this is g squared. Okay, so then I'm going to expand that, and I'm going to get 2x to the fifth plus 2x minus 4x to the fifth minus 4x to the third, all over x to the fourth plus 1, that quantity squared. And I'm going to end up with a minus 2x to the fifth minus 4x third plus 2x all over x to the fourth plus 1, that quantity squared. You guys agree? Oh, this should be a plus. I almost messed up. Do you guys see why it should be a plus? Just in case you don't see it, this times this would have given me a negative 4x to the third, but then there's a negative out front, so negative and negative become positive. Any questions? The odd silence is scary for me.
That's the answer. You expand the denominators.
Oh, so you don't need to expand the denominator. In this example here, we see that we're not going to be able to factor to cancel out the denominator. Typically, what you're going to want to do is leave it in that factored form because it potentially could cancel. Does that make sense? So you might be able to factor out an x to the fourth plus 1 out of the numerator, and then be able to cancel. So like let's say that in this example, if I would have done something like, and I'll do it in a different color just real quick. If this had been a square, then there would have been an x to the fourth plus 1 throughout that would have canceled. Does that make sense? Because then this would have ended up having 2x to the first, then there would have been a, but we're not ready for that yet because that involves another rule called the chain rule. So baby steps. So I would not expand the denominator to answer your question. Do you guys want to try one yourselves?
I had a question for this as well.
Okay, no problem.
Or in the third step, the last one you colored, so the negative, since it's minus the second part, it's the negative distributes to both parentheses, right?
So the negative distributes to one of them, not to both. Because it distributes to both. A product of two negatives is what?
Positive.
Yeah, so it's only to one of them.
Okay.
So the way that I typically do it, I'll show you. I'll write it on the side. So if I had done negative, and then it was, what was that? X squared minus 1, and then 4x to the third, the way I would have done it is I would have gone, okay, leave this guy out here, and then I would have gone 4x to the fifth minus 4x to the third, and now distributed, and there it is. That's the plus.
Okay.
Does that make sense?
Yeah.
Okay. I'll leave that there for you guys to look at. Do you want me to make you guys one for you to try?
Yes.
All right. So here we go. Let's make it ugly. Go ahead and find the derivative to this quotient. Yeah, let me know when you're ready. Any more time? All right, no problem. I'll give everybody 2 more minutes just to make sure, and then I'll start. All right, let me get started. So you guys can see this. So then the derivative of this, so the derivative of the numerator is going to be 3x squared plus 2x times the denominator minus the numerator times the denominator, the derivative of the denominator, which was going to be 2x, and then the denominator squared. Is everyone okay? Ooh, is everyone okay with this? Okay, cool.
So it's 3x squared just because you put the 3 in front and then just 3 minus 1.
Correct. Yeah, it's the power rule there. So this is f prime g f g prime and then g squared. Right, just so we have the rule. Okay. Then from here we're going to expand. Let's see if I can do that. 3x to the fourth minus 3x squared plus 2x to the third minus 2x minus 2x to the fourth minus 2x to the third minus 2x. All of that over x squared minus 1 squared, that whole quantity. And then let's see if we can clean that up. X to the fourth is it minus x cubed? I believe so. Then we have only one x squared term, so that's minus x squared, and then minus 4x, all over x squared minus 1, that quantity squared. Did I do that right?
I think
there's an x cubed.
the x cubed is canceled out.
Oh, yes, they're canceled out, not there. Okay, cool, thank you. That's good. So this is just x to the fourth minus x squared minus 4x. Yeah, that's right. We're good? And now you guys are correcting me. Very good. How do you guys feel? You guys are okay then? That's all I have for these two sections. So really it's about practicing, but that is these two sections. So just make sure that when you go to do these problems, they can be, yes, Christmas, nice. They can be tedious, and you can see where the algebraic mistakes can come into play, right? Yeah. The two rules, it's really not too bad. Like the two rules for this one that you need to know is this product, which will be f prime times g plus f times g prime, and then f over g prime is f prime times g minus f times g prime squared. So when you look at it, the product rule and the quotient, the numerator almost is the same except for it's a minus sign and then the denominator squared. So it's not too bad. Then you have the power rule from the previous section, and that's just about it. All right, I'm going to stop recording, and then if you guys have any questions in terms of homework or anything at all, I'll answer those questions for you guys. I just don't want to make this video too crazy long. Okay? So let me find where my recording is. Here we go.